Position of the Solar System within the Milky Way. Diagram of the Milky Way with the position of the Solar System marked by a yellow arrow and a red dot in the Orion arm, the dot roughly covering the large surrounding celestial area dominated by the Radcliffe wave and split linear structures, formerly Gould belt. The Solar System is located in the Milky Way, a barred spiral galaxy with a diameter of about 100,000 light-years containing more than 100 billion stars. The Sun resides in one of the Milky Way's outer spiral arms, known as the Orion Cygnus arm or local spur. The Sun lies about 26,660 light-years from the galactic center, and its speed around the center of the Milky Way is about 220 km per second, so that it completes one revolution every 240 million years. This revolution is known as the Solar System's galactic year. The solar apex, the direction of the Sun's path through interstellar space, is near the constellation Hercules in the direction of the current location of the bright star Vega. The plane of the ecliptic lies at an angle of about 60 degrees to the galactic plane. The Solar System's location in the Milky Way is a factor in the evolutionary history of life on Earth. Its orbit is close to circular, and orbits near the Sun are at roughly the same speed as that of the spiral arms. Therefore, the Sun passes through arms only rarely. Because spiral arms are home to a far larger concentration of supernovae, gravitational instabilities, and radiation that could disrupt the Solar System, this has given Earth long periods of stability for life to evolve. However, the changing position of the Solar System relative to other parts of the Milky Way could explain periodic extinction events on Earth, according to the Shiva hypothesis or related theories, but this remains controversial. The Solar System lies well outside the star-crowded environs of the galactic center. Near the center, gravitational tugs from nearby stars could perturb bodies in the Oort cloud and send many comets into the inner Solar System, producing collisions with potentially catastrophic implications for life on Earth. The intense radiation of the galactic center could also interfere with the development of complex life. Stellar flybys that pass within 0.8 light-years of the Sun occur roughly once every 100,000 years. The closest well-measured approach was Schultz's star, which approached to 52 plus 23. Minus 14 Kau of the Sun, some 70 plus 15. Minus 10 Kau, likely passing through the outer Oort cloud. Celestial neighborhood. Beyond the heliosphere is the interstellar medium, consisting of various clouds of gases. The Solar System currently moves through the local interstellar cloud, here shown along with neighboring clouds and the two closest unaided visible stars. The Solar System is surrounded by the local interstellar cloud, although it is not clear if it is embedded in the local interstellar cloud or if it lies just outside the cloud's edge. Multiple other interstellar clouds also exist in the region within 300 light-years of the Sun, known as the local bubble. The latter feature is an hourglass-shaped cavity or superbubble in the interstellar medium roughly 300 light-years across. The bubble is suffused with high-temperature plasma, suggesting that it may be the product of several recent supernovae. The local bubble is a small superbubble compared to the neighboring wider Radcliffe wave and split linear structures, formerly Gould belt, each of which are some thousands of light-years in length. All these structures are part of the Orion arm, which contains most of the stars in the Milky Way that are visible to the unaided eye. The density of all matter in the local neighborhood is 0.097 plus or minus 0.013 mpc-3. Within 10 light-years of the Sun there are relatively few stars, the closest being the triple star system Alpha Centauri, which is about 4.4 light-years away and may be in the local Bubbles G cloud. Alpha Centauri A and B are a closely tied pair of Sun-like stars, whereas the closest star to Earth, the small red dwarf Proxima Centauri, orbits the pair at a distance of 0.2 light-year. In 2016, a potentially habitable exoplanet was found to be orbiting Proxima Centauri, called Proxima Centauri b, the closest confirmed exoplanet to the Sun. The next closest known fuses to the Sun are the red dwarfs Barnard's star at 5.9 light-years, Wolf 359 7.8 light-years, and Lalande 21185 8.3 light-years. The nearest brown dwarfs belong to the binary Lumen 16 system 6.6 light-years, and the closest known rogue or free-floating planetary mass object at less than 10 Jupiter masses is the sub-brown dwarf WISE 0855-0714 7.4 light-years. Just beyond at 8.6 light-years lies Sirius, the brightest star in Earth's night sky, with roughly twice the Sun's mass, orbited by the closest white dwarf to Earth, Sirius B. Other stars within 10 light-years are the binary red dwarf system Luyten 726-8 8.7 light-years, and the solitary red dwarf Ross 154 9.7 light-years. The closest solitary Sun-like star to the Solar System is Tau Ceti at 11.9 light-years. It has roughly 80% of the Sun's mass but only about half of its luminosity. The nearest and unaided visible group of stars beyond the immediate celestial neighborhood is the Ursa Major moving group at roughly 80 light-years, which is within the local bubble, like the nearest as well as unaided visible star cluster the Hyades, which lie at its edge. The closest star-forming regions are the Corona Australis molecular cloud, the Rho Ophiuchi cloud complex and the Taurus molecular cloud. The latter lies just beyond the local bubble and is part of the Radcliffe wave. Comparison with extrasolar systems. Compared to many extrasolar systems, the Solar System stands out in lacking planets interior to the orbit of Mercury. The known Solar System also lacks super-Earths, planets between 1 and 10 times as massive as the Earth, although the hypothetical Planet 9, if it does exist, could be a super-Earth beyond the Solar System as we understand it today. Uncommonly, it has only small rocky planets and large gas giants, elsewhere planets of intermediate size are typical, both rocky and gas, so there is no gap, as seen between the size of Earth and of Neptune, with a radius 3.8 times as large. As many of these super-Earths are closer to their respective stars than Mercury is to the Sun, a hypothesis has arisen that all planetary systems start with many close-in planets, and that typically a sequence of their collisions causes consolidation of mass into few larger planets, but in case of the Solar System the collisions cause their destruction and ejection. The orbits of Solar System planets are nearly circular. Compared to other systems, they have smaller orbital eccentricity. Although there are attempts to explain it partly with a bias in the radial velocity detection method and partly with long interactions of a quite high number of planets, the exact causes remain undetermined. Humanity's perspective. Harrison H. Schmitt, an astronaut in the Apollo 17 mission, with the Moon and Earth in the background. Humanity's knowledge of the Solar System has grown incrementally over the centuries. Up to the late Middle Ages Renaissance, astronomers from Europe to India believed Earth to be stationary at the center of the universe and categorically different from the divine or ethereal objects that moved through the sky. Although the Greek philosopher Aristarchus of Samos had speculated on a heliocentric reordering of the cosmos, Nicolaus Copernicus was the first person known to have developed a mathematically predictive heliocentric system. Heliocentrism did not triumph immediately over geocentrism, but the work of Copernicus had its champions, notably Johannes Kepler. Using a heliocentric model that improved upon Copernicus by allowing orbits to be elliptical as well as circular, and the precise observational data of Tycho Brahe, Kepler produced the Rudolphine tables, which enabled accurate computations of the positions of the then known planets. Pierre Gassendi used them to predict a transit of Mercury in 1631, and Jeremiah Horrocks did the same for a transit of Venus in 1639. This provided a strong vindication of heliocentrism and Kepler's elliptical orbits. In the 17th century, Galileo publicized the use of the telescope in astronomy. He and Simon Marius independently discovered that Jupiter had 4 satellites in orbit around it. Christian Huygens followed on from these observations by discovering Saturn's moon Titan and the shape of the rings of Saturn. In 1677, Edmund Halley observed a transit of Mercury across the Sun, leading him to realize that observations of the solar parallax of a planet, more ideally using the transit of Venus, could be used to trigonometrically determine the distances between Earth, Venus, and the Sun. Halley's friend Isaac Newton, in his Magisterial Principia Mathematica of 1687, demonstrated that celestial bodies are not quintessentially different from earthly ones. The same laws of motion and of gravity apply on Earth and in the skies. (142). The term «solar system» entered the English language by 1704, when John Locke used it to refer to the Sun, planets, and comets. In 1705, Halley realized that repeated sightings of a comet were of the same object, returning regularly once every 75 to 76 years. This was the first evidence that anything other than the planets repeatedly orbited the Sun, though Seneca had theorized this about comets in the 1st century. Careful observations of the 1769 transit of Venus allowed astronomers to calculate the average Earth-Sun distance as 93,726,900 miles, 150,838,800 kilometers, only 0.8% greater than the modern value. Uranus, having occasionally been observed since antiquity, was recognized to be a planet orbiting beyond Saturn by 1783. In 1838, Friedrich Bessel successfully measured a stellar parallax, an apparent shift in the position of a star created by Earth's motion around the Sun, providing the first direct, experimental proof of heliocentrism. Neptune was identified as a planet some years later, in 1846, thanks to its gravitational pull causing a slight but detectable variation in the orbit of Uranus. In the 20th century, humans began their space exploration around the Solar System, starting with placing telescopes in space. Since then, humans have landed on the Moon during the Apollo program. The Apollo 13 mission marked the furthest any human has been away from Earth at 400,171 kilometers, 248,655 miles. All 8 planets have been visited by space probes. The outer planets were first visited by the Voyager spacecraft, one of which, Voyager 1, is the furthest object made by humankind and the first in interstellar space. In addition, probes have also returned samples from comets and asteroids, as well as flown through the Sun's corona and made flybys of Kuiper belt objects. 6 of the planets, all but Uranus and Neptune, have or had a dedicated orbiter. The future of the Solar System is hard to predict with certainty, as it depends on various factors such as discoveries in astronomy and space exploration, advancements in technology, and changes in economic and political priorities. However, based on current knowledge and plans, here are a few things that might happen in the future of the Solar System. Exploration of the outer Solar System. In the coming decades, there are plans to send missions to explore the outer reaches of the Solar System, including the gas giants Jupiter and Saturn, and their moons. These missions could help us learn more about the origins of our Solar System and the conditions for life beyond Earth. Mining the asteroids. With the increasing demand for resources such as precious metals and water, there are plans to mine asteroids for their valuable resources. This could potentially be a lucrative industry in the future and could also help reduce the demand for resources on Earth. Colonizing the Moon. With the recent successful missions to the Moon, there are plans for establishing a permanent human presence on the lunar surface in the coming years. This could serve as a stepping stone for future missions to Mars and beyond. Mars exploration and colonization. Mars is considered the next frontier in space exploration, and there are plans to send human missions to the Red Planet in the coming decades. This could lead to the establishment of a permanent human settlement on Mars and could also help us learn more about the potential for life on other planets. These are just a few examples of the potential future of the Solar System. However, it is important to note that these plans and predictions are subject to change based on future developments and advancements in technology. Thanks for watching. Please like and subscribe.